because the pressure gradient force is getting weaker and weaker. And we call that process cyclolysis. Lysis being a suffix that means something like death. Oh, and I have this cheesy animation here where the logo gets smaller and smaller. Okay. Cyclolysis and cyclogenesis are like the yin and yang of meteorology. Just like life, cyclolysis is the natural end of these cyclones. Once you start the cyclone, he can only die. Cyclolysis and cyclogenesis are couples. They go together. Early in the life of the cyclone experiences cyclogenesis, where the cyclone is strengthening as its pressure gets lower and lower. And that's going to happen because because of the jet stream that has positive vorticity advection causes divergence. There's less and less air above the cyclone aloft. The cyclone at the surface. The aloft is less and less air, which means from the point of view of the cyclone down at the surface, there's less weight above it than there was before, and the pressure gets lower and lower. Cyclolysis, on the other hand, happens once that cyclone gets going. He's going to go through his life cycle. Oh, he's a nice open wave for a while, but sooner or later that cold front's going to catch up with the warm front, because the cold fronts only move faster than the warm fronts do, which means sooner or later that cold front will catch the warm front, make it an occluded front. Crap. Once you've got an occluded front, you got a problem. You're going to start experiencing cyclolysis. We cheer for the cyclone here. We've got a problem. Now the cyclone has got cyclolysis. He's getting weaker because his pressure is going back up. What's going on? It's happening because there's no longer a jet stream above the cyclone. Why would there no longer be a jet stream above the cyclone? Because there's no temperature gradient near the cyclone. Both sides of the occluded front are cold. By the thermal wind relationship, we know that the jet stream isn't going to be there anymore. It's going to be someplace else. And therefore, we're going to have no positive vorticity advection anymore, which means no divergence anymore, which means no reason for the cyclone to be there anymore. As pressure will slowly go back up towards normal, and sooner or later, it takes, nobody can find it anymore. Pressure is no longer low, the fronts are no longer strong. Let's do some examples. Here is a map of the weather one day at the level of the jet stream. If you can't quite see the arrows, these are isobars with these white lines on here. So they are showing you that there's like higher pressure over here, there's lower pressure over there. The winds are flowing parallel to the isobars because it's jet stream level. The flow is geostrophic. And the colors on the map indicate the speed of the wind. And you can see that the wind speeds are very, very high in this sort of U-shaped region right here, which is winds of at least 140 miles per hour. That's pretty damn fast wind. That's a trough. See how the winds were headed to the south, and then they made a left turn, and they're headed back to the north? That's a trough. That's why I drew it on here with a dashed line. There's also a ridge back here, where the winds were headed to the north, and then they turn back down towards the south. So here's a trough. That's a hell of a trough, by the way. He's a pretty big trough. And if we look at him, and we say, I think that there should be positive vorticity in the trough, because the flow is turning in a counterclockwise way. Well, as I told you, vorticity is just a number. We can make a map of vorticity. Oh, I apologize, got the same damn red versus black problem on this projector. I gotta remember to quit doing that. But we can make a map of vorticity, and the numbers for the vorticity in this region are around 25. The numbers out here are like 0. This is a big area of positive vorticity on here. For that matter, positive vorticity advection is just a number. We can do the math. It's not really something mortals can do, but computers can do it lickety-split. And so we can make a map of positive vorticity advection, and we can see that the numbers are quite great right here near Detroit in that case. There's a lot of positive vorticity advection going on out there. And in fact, that is, when I look at a surface map, these contours on here are the pressure, and our center of our cyclone, our area of low pressure, is right there in northern Indiana near Detroit. And you can see we've got a narrow band of clouds through our cyclone. There's our cold front. Here's the rising motion near the cyclone itself. It's beautiful. It works so lovely. Let's do another example that's a little less ideal. Here's another trough. Winds are headed to the south, and then they make a left turn and head off towards the north. It's a big trough in the jet stream. So we would expect positive vorticity in the trough itself. And out here ahead of the trough, where the flow is going straight, then apparently we have positive vorticity advection. The air that is coming towards this region over Kansas and Missouri is apparently experiencing, it currently has no vorticity, and the air that's coming has a lot of vorticity. That's positive vorticity advection. And we apparently need to lose that spin, and in fact, in order to do that, we have to produce positive vorticity advection and make a cyclone at the surface. Okay. I would wholeheartedly agree that this material is a smidge overwhelming. And I don't like it when it works out that this happens right around spring break. But we will have we do already have lots of resources available to you on Blue Line, like the PowerPoint, like a video about the PowerPoint, like lots of handouts, etc. I would recommend making good use of them. We just have a little bit of new material on Thursday, as well as your homework stuff that's due, and then we kind of put all this unit together. All right, yes? You send me an email, I will take some of that stuff. I'll put it up for everything. Yeah, that's a great idea.
So they said it was like,